Hello everybody and welcome to my talk. My name is Rokicki and I'm a PhD student in Univren CNRS IRISA. In this video, I will present you our work called Port Contention Goes Portable, Port Contention Side Channels in Web Browsers. It was joint work with Clémentine Maurice at Univlil CNRS in RIA, as well as Marina, Botvinnik and Yossi Oren from Ben-Gurion University of the Negev. In this video, we will show you the first implementation of port contention inside the browser sandbox. We will also give two examples to illustrate the threats posed by these side channels. We'll start with a little bit of background on microarchitectural attacks. They are a subset of timing attacks where we exploit subtle timing differences caused by optimizations at the microarchitectural level to infer secrets. Of course, cache attacks are the most famous, but actually most microarchitectural optimizations can be targeted, and in our case, the CPU ports here. Our attack relies heavily on hyperthreading, or SMT. It is the name of the simultaneous commutation technology of Intel. Basically, what it means is that in order to boost parallelism and take as much advantage as the limited resource of hardware as possible, each one of the physical cores on CPUs are sharing several logical cores, often two for mainstream computers. But there is an abstraction at the OS level, meaning that if you have 4 physical cores, each split in 2, your computer will act as if you have 8 cores total. But at the hardware level, hardware resources of 2 logical cores sitting on the same physical core are shared, including the execution pipeline, for instance. The execution pipeline is the process that fetches the instructions of the compiled code and executes them somehow. So basically here we have 2 threads, thread 1 and thread 2, on 2 different logical cores sitting on the same physical core because they use the same execution pipeline. The decoder will fetch instructions, so x86 instructions or assembly instructions, if you will. And at this point, the instructions are very variable in size and in the resources they need to be run. So the decoder will try to uniform that by translating them into micro-operations to optimize out-of-order computations. It will be then forwarded to the execution engine. Now, the execution engine is a set of execution units, and each of these units is highly specialized, meaning you have execution units for algebraic computation, for memory operation, etc. So basically, each UOP has to go to the associated execution units. And to do so, the scheduler will send the micro-operation to CPU ports. Here you can see them, P0 to P7 for a Skylake computer. So each one of the CPU port is also highly specialized because it's kind of the doorway to the associated execution units. So port 0 here is specialized in AES NI computation, among other. Port 1 does all the algebraic computations. Port 2, 3 handles memory writes and reads. So UOPs are dispatched to this port, who will act as queue, letting by a single micro-operation per cycle. And this decomposition of instructions into micro-operations is deterministic. We know the port usage of native instructions. And at the very core of port contention, as theorized by Aldaya et al. In 2019, it's just using these ports as a bottleneck because they can let by a single micro-operation per cycle. So if in this scenario we have an attacker and the victim, 2 of them sitting on a single physical core, the attacker will repeatedly call a specific instruction creating port 1 micro-operation, so it will fill the port 1 queue with his instructions. In this scenario, he's alone to do it, so everything is executed in a row, resulting in a fast execution time. But in the second scenario, by any chance, the victim will emit a micro-operation that also goes on port 1, and because it's shared, it will sit in the same queue, hence delaying some of the attacker instructions, attacker micro-operations, resulting in a slower execution time. And it's basically the core of port contention, where we can monitor the port usage of the victim just by using ports, here port 1, but it can be done for any ports, as a bottleneck. This attack has a lot of prerequisites as of microarchitectural attacks. The first one is quite logical. Attacker code must run on the victim's hardware because it's the sharing of the hardware that allows the attack. If we do not have the same hardware, we cannot use it as a bottleneck to monitor the victim. But this prerequisite is even stronger in the case of port contention because the attack relies on hyperthreading. It's the same core attack. So attacker and victim must be on the same physical core, otherwise they would not share the execution pipeline, so they will not share the cores. Also, finally, attacker must have access to high resolution timers. We are talking about a few cycles of differences, so we need timers with a resolution of around 10 nanoseconds mainly. No, I've mentioned that our attack runs in the browser, so we'll talk a bit of the languages we use to do it because they are a very important factor in this paper. We will talk about two client-side code language. So first, JavaScript and WebAssembly, both are client-side scripting language. So basically what it means is that when you visit a website, everything is not run on the server because it will be so slow and there would be delay. So you actually download generally a JavaScript script and you read it on your own machine. This allows for faster computation. But because you cannot really trust all and check all the JavaScript code you run on your hardware, the code runs in a very heavily restricted sandbox, both for JavaScript and WebAssembly, where it doesn't have access to the file system, obviously. It doesn't have access to native instructions. It doesn't have access to virtual addresses, for instance. And there are a lot of restrictions put on JavaScript and WebAssembly. So they are very high-level languages. The main difference between the two is that JavaScript is even a higher level language because it's compiled just in time. And we don't really know what it does at the lower level. All the instructions are heavily optimized, so it can be really tricky to run microarchitectural attacks with it. However, WebAssembly is compiled directly from another language, for instance, C, C++, but there's also a text format to write WebAssembly directly. And this grants us way more control on what we do because it provides smaller, more atomic instructions. So it's a bit lower level, even though it's still sandboxed. So why would we want to implement port contention with these languages? It's just to have an extension of the threat model because client-side language is run on the client's hardware. So basically, it fills the first contention of the first prerequisite of contention. So basically, we can run port contention attack on the victim's hardware quite easily because every user that visits a malicious website or even a legit website with a malicious advertisement can fall victim to port contention attacks. So this is dramatical enhancement of the threat surface of port contention. However, it comes with challenges, 3 of them we isolated. The first one is that JavaScript or WebAssembly does not offer core control. We cannot know at any given point on which core we are running, and we cannot control it either. Secondly, we don't have access to high-resolution timers. Finally, maybe the biggest challenge is that, well, both languages are very high-level languages and are sandboxed, and we don't know the translation of our WebAssembly code to at least x86 instructions and even less micro-operations. We don't know the port usage of our code. To address these challenges, we'll do it iteratively. So first, core control. I've mentioned that JavaScript does not have core control, which is critical for our attack because we need the attacker and the victim to sit on the same physical core. And if we cannot control nor know on which core we are running, it cannot be done. But we can exploit the operating system scheduler. It's basically the system that dispatches all processes on different physical and logical cores. And basically, logically, to boost parallelism, it tries to balance the workload on all physical cores. So basically what we do is we multi-thread our attack. We create, for instance, if we have 4 physical cores, we'll create 4 different attacking JavaScript web workers. And because they are quite computational heavy, there is a high chance that each physical core will retrieve an attack thread, so that at least one physical core will hold both the victim and the attacker. For high-resolution timers, a few years ago, to prevent timing attacks and mainly Spectre, browser removed access to JavaScript high-resolution timers and added jitter to the measurements. However, academics have shown that it's not such an efficient countermeasure because we can still build auxiliary timers with a resolution of several nanoseconds. So I will spare you the details, but in this paper we will use shared array buffer as timers. So now we have C1 and C2 handled, so we need to handle C3, but we still don't even know if it's possible to do port contention. We don't know if it's fast enough in the browser. We don't know if it's fast enough. We have no idea of the port usage of WebAssembly instructions. So to fix that, we built an automated framework called PC Detector. Basically what it does is that it compares 244 WebAssembly instructions with native instruction because we know the native port usage of native instructions. So the experiment is quite simple. We have 2 components, a native spammer and a web tester. The native spammer is just a loop calling a specific instructions many times. And the web tester does the same but with WebAssembly instructions and will time the execution it takes to run these instructions. So for each WebAssembly instructions, we run the following experiments. The first one is just a control experiment where the web script runs alone in the browser. So in that case, we shouldn't have any trace of contention. And the second one is a test for contention on port, let's say 1. So in that case, the native spammer will repeatedly call an instruction creating contention on port 1. And both the spammer and the tester will run together on the same physical core. So in that case, if we observe that the execution time of the web tester is slower than the control, it means that there is contention on port 1 in that case. And if it's just as fast as the control experiment, it means it does not have a port 1 usage. So we test all WebAssembly instructions with ports 0, 1, 2, 3, 5, and 6. And the results are great because we tested over 200 instructions and we found over 80 instructions creating contention. Even better than that, we found that we could target 4 different ports with port contention, so namely 0, 1, 5, and 6. And for some reasons, all the instructions do not create the same quality of contention. So we found the best one, which is i64.remu. I don't really know what it does, but it just creates nice contention on port 1. Also, funnily enough, because of the changes in the microarchitecture, mainly between generations, some instructions create contention on several generations and not on others. So there are a few differences in the results on different CPU generations. That's why we wanted to build an automated framework just to see the difference it would be and to have a nice evaluation. So now that we've handled the 3 challenges and we know the port usage of our instructions, we wanted to build examples to illustrate the threat of web port contention. The first one is just an artificial example of a side channel attack, where we have a victim, which is just a native sender running its own life, and it executes different branches based on a secret, and we want to know this secret. The first branch of secret 0 creates contention on port 1 by repeatedly calling pop count, and the second branch, branch 1, executes VP broadcast D, creating contention on port 5. So now our attacker, which stands in the JavaScript sandbox inside of the browser, will try to guess the secret based on the branch taken and the contention created. So by monitoring port contention on port 1, if it detects contention, it knows that the secret is 0. But if it detects contention on port 5, it knows that the secret is 1. A very important factor to notice here is the minimal number of instructions in a branch we can detect, because it's basically your spatial resolution, which is highly important in side channel attacks. And this works quite great for a side channel attack in the browser. Here you can see we repeated the previous experiment several times in a row, and you can say that the result is 11011001. And we are able to detect up to 1,000 native instructions in a single trace, which is basically our spatial resolutions. And this resolution is on par with web-based cache attacks, the best one being Prime+Probe. So it's really good results. But what's even better is that Prime+Probe has a theoretical limit to its spatial resolution due to the nature of the attack. However, our port contention side channel could theoretically get a better resolution, but we have an experimental limit to 1,000 native instructions because of poor quality timers. But we implemented a custom timer with a custom browser with better timers, and we were able to detect up to 200 native instructions in a single trace setting. The second example we want to provide is a covert channel. Here we have a native sender communicating with a web receiver through CPU ports. So they both send one to receive. They both create contention on port 1 to send a 1, and they do nothing to send a 0. It's a very threatful model in the web browser because it would allow to break the isolation of the JavaScript sandbox and, for instance, exchange cookies, monitor the user. So it's a really big breach in the security of browsers. And the results are quite good. We found a 200 bit per second bandwidth with only 6% of frame loss. So to the best of our knowledge, it is the best bandwidth for any covert channel in the browser currently. We also, to prove the flexibility of this covert channel, implemented other settings. The first one where the sender sits inside of a virtual machine. So we have an added stack of virtualization, and we can still communicate through CPU ports. It could be a very interesting model, for instance, for malware analysis, where you analyze the malware inside of a sandbox to protect yourself. It could also be used on public clouds, where you have many different virtual machines that share the same physical hardware. The second setting is quite cool. It's from browser to browser. So this means that two different tabs in the browsers could communicate with one another, which they shouldn't be able to do. And for instance, exchange session cookies or exchange information about the browsing. It's really dreadful. And it even works cross-browser. So from instance, from Firefox to Chrome, we can make the two processes communicate with one another. So now that we've illustrated the threat of port contention, we wanted to do a quick overview on countermeasures that have been proposed by industrial or academics. At the hardware level, the easiest solution would be to disable SMT, but it's not a very subtle countermeasures, as it has a very high performance cost, about 15% of performance overhead. But a better approach has been proposed by using dynamic sharing of the resources, maybe temporal, where certain resources are available to a certain logical core only at a given time, and it's never shared, or even more complicated ways. At the OS level, some academics have mentioned port-independent code, meaning that the port usage of the victim does not depend on the secret, but it's not really scalable, as we have to modify all the code base previously existing. Another solution would be port-aware scheduler, meaning that the OS scheduler do not put untrusted process on the same physical core as critical sensibility computation. Finally, at the browser level, there was no proposition specifically aimed at port contention, but for most microarchitectural attacks, browser vendors have tried to remove access to high-resolution timers, which does not work so well as we've shown. And they've tried to add more isolation, mainly at the process level, but it does not affect port contention, as it's only affecting shared memory, not, well, shared execution pipeline. So to conclude, in this talk, we've presented the first implementation of port contention inside of the browser. We also showed that with our attack, we can have the fastest covert channel exiting in the browser, as well as a very high spatial resolution. And it's a really, to me, it's a really critical attack, as it breaks the isolation paradigm of the browser, because in this setting, cross-origin communication is possible through tabs or through browsers, even through virtualized environments. So thank you for listening to my talk. I hope you've had as much fun listening to the presentation as we've had fun making the paper. If you have any questions, you can contact me at this mail here. I would greatly appreciate if you would read the paper for more technical details. You can even find all the code used for the experiments. It's been publicly released on this GitHub. Thank you very much and goodbye.